Okay, so let's continue talking about the bistable equation and how we derive traveling wave solutions. Remember that the canonical ODE for the bistable equation has 3 fixed points, 2 stable, 1 unstable. And as we discussed last time, if we couple together adjacent bistable ODEs, then we can propagate the states of one system to another. Okay, so what do I mean by this? So if we consider diffusive coupling, okay, we essentially link the adjacent steady states. Then here we have U may be 1 here, right? Way down here may be -1. Here may be 0. And here's our x variable. At each point, right, this is going to put tension on this state here to pull it up. This will then pull this state up. This will pull this state up. And then the question is, this state here that's below 0, will it get pulled up or will it get pulled down? That depends on the surrounding values of U that are adjacent or close to that particular U value in that case. Okay, so we can do this in a model with discrete space, but in the continuum limit, the analysis is easier. So the idea here is that if one of these states is sort of up, okay, it should enact a sort of pull on states that are down if they're close enough together. Okay, so the full bistable Pde now is going to involve U sub t now plus some diffusive term plus some nonlinearity. Okay, and I'm not going to use the particular nonlinearity that we talked about before. I'm going to use a slightly more general one. Okay, and in particular, the last function we used was a cubic. You use a cubic nonlinearity because we usually like to work in positive values of U. We're going to have a cubic that has 3 non-negative roots, okay? 0, 1, and A. And so if we draw this function, it's going to look something like this. So here's 1, here's U, here's A, and then here's 0, okay? Because f prime of 0 is less than 0, that means that U equals 0 is stable. Here, f prime of A is greater than 0, that means U equals A is unstable. And here we have U equals 1, right? F prime of 1 is less than 0, so U equals 1 is stable, okay? So just like before, we have 2 stable fixed points, but we can play a bit with this parameter A in order to sort of change the strength of attraction of those fixed points, okay? All right, so what are we going to do? Well, you'll forgive me, I'll sort of skip the preliminaries and just say that we're going to assume traveling wave solutions, okay, of specific speeds are predicted for this model, okay? So I'm going to set u to be equal to v of xi, v is equal to x minus st, okay? And so if we plug that into our PDE here, we're going to get minus SV prime is equal to V prime prime plus F of V. Okay. Now, you can write this as a system, a 2D system, which is just going to be V prime equals W, W prime equals minus SW minus F of V. Okay. And let's just keep this general for now, just so we can carry around an F of V, okay? In general, right, F doesn't have to be this cubic nonlinearity. It could really be anything that has 3 intersection points like this. So you could have another nonlinear function that just intersects the u-axis twice, or 3 times, excuse me. The only thing you need is that F of u has 3 zeros, okay? And we're going to make those zeros 0, A, and 1. And so in that case, our equilibria are going to be VW equals 0, 0, okay? A, 0, and 1, 0, okay? All right, so what do we usually do when we're doing faceplate analysis? We take these equilibria and then we look at their stability. So in order to kind of dissect this, okay, let's look at the stability of each of these fixed points by computing the Jacobian. And the Jacobian in this case is 0, 1, minus f prime of v minus s, okay? So for v is equal to 0 or 1, that's our two limiting, those are two fixed points on the left and right ends, right? We have that minus f prime of v is greater than 0, since we know that f prime of v should be less than 0 for those to be stable fixed points in the original bistable equation, okay? So for some s less than 0, right? So if we look at our fixed points, then they have eigenvalues that are given by a half minus a half plus minus s squared minus 4 f prime of v. Okay. And these then are going to, because f prime of v minus f prime of v is positive, that means this thing is going to be bigger, this whole thing is going to be bigger than s squared, okay? So then this is going to have a positive and a negative real eigenvalue. And so we are going to have a saddle point at each of these, okay? So how is that going to work, okay? Well, the analysis that you have to do in this case is quite a bit more involved than before, okay? But the idea is that at s equals 0, you're going to have a homoclinic orbit like this, emanating from the saddle at 0. You have a center right here. And I'm going to call this piece right here Mu. That's our unstable manifold. And then so this is at 0, this is at A, and this is at 1. And then we're going to have another manifold that's called MS that is going to approach this saddle up here, okay? So this manifold approaches this saddle point. This manifold sort of, for now, it wraps around here, but as soon as we change S, we're going to lose this homoclinic here, okay? So Mu is going to be an unstable manifold coming from 0, 0. MS is going to be a stable manifold coming from the point 1, 0, or coming to point 1, 0. Okay, so what happens as we change S? So for some value of S less than 0 now, okay, there's going to be some value of S, okay, where this manifold and this manifold come together and they make a heteroclinic orbit, okay? So what happens with that particular value of S is that we make a heteroclinic right here that's going to represent our traveling front solution. And then we have a manifold that emanates out that way, and then we have this manifold here, and then we have this manifold here, okay? So what you can show, and I'm not going to show it here, this is actually a many-page paper that showed this, is essentially there's a way to sort of gradually change S so that eventually these manifolds meet as you change your parameter. It's going to change the flows of your phase plane. Okay, so let me kind of summarize what we're saying here. At S equals 0, there exists some standing pulse, and that's our homoclinic orbit. Okay. And then for some S less than 0, there exists a traveling front, and we're calling that a heteroclinic, right? And in particular, we can calculate this explicitly when we have a cubic, when f of u is equal to u, 1 minus u, u minus a, okay? But in general, okay, f of u, we use the above, it's called a shooting argument, okay? And the idea is that you shoot this stable manifold, this unstable manifold from here, and you see if it ends up hitting your other saddle. If it doesn't, then you adjust, right? And so the idea here is that if I just draw these two saddles, right, if I shoot and it overshoots, okay, this would mean that S is too negative in this case. If I shoot and it doesn't quite hit it, right, then this would mean S is not negative enough, okay? So right in between, okay, we're going to have a Goldilocks value of S where you can shoot this manifold from here and it hits your target. And that's used commonly in ODEs and PDEs as sort of shooting approach. It can be automated numerically, although you can construct proofs using a shooting argument as well. Okay, so the idea is to iterate for S greater than S star and S less than S star until S is roughly equal to S star. Okay, so this is your S star. This is S less than S star, and this is S greater than S star. Okay, so that's your theorem. If you want to read about it, it's in Shear. Okay, theorem essentially is suppose that F satisfies the integral from 0 to 1 of f of y dy is less than 0. Okay, then there exists an S less than 0 such that your bistable equation has a traveling wave solution. U is equal to v of xi such that v is less than equal infinity is equal to 0, and v at plus or minus, sorry, at plus infinity is equal to 1. Okay, so the idea is that you've constructed a traveling wave that's propagating that way because S is less than 0. Okay, and the proof, as I said, it's in Shear and Levy. Okay, it uses the well-posedness of the phase plane system. So our stable and unstable manifolds deform continuously, okay? And that's important to the shooting argument, right? So basically, as I change my parameter S, my stable and unstable manifolds should deform continuously until they meet each other and they make this nice heteroclinic trajectory, okay? So yeah, there must be some S for which those two are going to meet each other. Okay, so read that if you like. This should give you some intuition behind the traveling wave problem. Let's conclude by actually solving for this